All right, let's dive right in. We're about to unpack one of the most bizarre detective stories in all of modern physics. It's a case about disappearing particles, a perfect theory that suddenly had a crack in it, and a solution that, believe it or not, reveals the actual geometry of reality itself. So welcome to the strange and wonderful world of neutrino oscillations.
So this was the central mystery, right? For decades. Our understanding of the sun was rock solid. We could predict with incredible precision how many particles called neutrinos should be streaming towards Earth every single second. The problem? When we actually went to go look for them, our numbers were wrong. And not just a little wrong, they were deeply, fundamentally, unsettlingly wrong.
Yeah, we only found 1/3 of them. 1/3. For every 3 neutrinos that the sun made, 2 of them had just vanished, gone without a trace by the time they reached our detectors here on Earth. Now, this wasn't some small measurement error. This was a full-blown crisis. It meant either we didn't understand stars or we didn't understand the particles themselves.
So let's start right where it all began, with this massive puzzle known to everyone in the field as the solar neutrino problem.
You know, the answer, when it finally arrived, was so much weirder than anyone could have guessed. The particles weren't gone at all. They were masters of disguise, literally changing their identity during that 8-minute journey from the sun to us.
So who are these little shape-shifting culprits? To really get how they pull off this incredible trick, we need to properly meet the ghost particles themselves.
Okay, so neutrinos come in 3 distinct types, or as physicists call them, flavors. There's the electron neutrino, the muon neutrino, and the tau neutrino. Now, here is the crucial point. The nuclear reactions happening inside the sun only produce electron neutrinos. That's it. So naturally, that's what scientists on Earth were looking for. They built these incredibly sensitive detectors specifically designed to see electron neutrinos. And that's exactly why they kept coming up short.
And here's where the quantum weirdness really kicks in. A neutrino is born with a specific identity, its flavor. So in the sun's case, it's an electron neutrino. But, and this is the whole game, it doesn't travel with that same identity. As it zips through space, it's actually a mixture, a weird combination of 3 different mass states. This fundamental mismatch, right, between how a neutrino is made and how it moves, well, that's the engine for everything that's about to happen.
Now, this whole quantum confusion thing sounds impossibly complicated, I know. But there's an incredibly cool and intuitive way to visualize it, and it just uses simple geometry. So that's what we're going to explore in Section 3, Rotation in Flavor Space.
Let's just build a mental model here. Picture a 3D space, with an X, Y, and Z axis. But instead of X, Y, and Z, each axis represents one of the 3 flavors. So let's say the horizontal axis is electron, the one coming out towards you is muon, and the vertical axis is tau. We'll call this our flavor space.
Great. Now, a neutrino state can just be represented as a simple arrow, a vector, in this space. And since the sun makes a pure electron neutrino, that vector starts out pointing perfectly, 100% right along the electron axis. At the moment it's born, there's a 100% chance you'll measure it as an electron neutrino. Makes sense. But here is the big twist. That mismatch we were just talking about, we can visualize it as a second set of axes, the mass axes, that define how the neutrino actually travels through space. And the key insight, the whole shebang, is that these mass axes are tilted. They're rotated relative to the flavor axes that we use to measure them. So because the travel rules are based on this tilted set of coordinates, the neutrino state vector has no choice. It's forced to rotate as it flies. It starts out pointing at electron, but as it travels, that arrow starts to swing, pointing a little bit towards muon and then a little bit towards tau, just cycling through all 3. It's not some magic transformation, it's just rotating through this abstract space.
So we have this really clean geometric picture, right? An arrow spinning around. But how does that translate into the hard math of physics? How do we get from a picture to a prediction? Well, that brings us to Section 4, the geometry of probability.
Okay, I know this formula looks super intimidating, but trust me, it's just our picture put into mathematical terms. Seriously, that theta symbol, the mixing angle, that's literally the angle of the tilt between the flavor and mass axes. That delta m squared, the mass difference, that just tells you how fast the vector rotates. L over E, distance over energy, that's just how far along its rotation it's gone. And the probability part, the sine squared, that's just the length of the vector shadow projected onto one of the other axes. That's all it is. It's all just geometry.
And the source material really drives this home.
connecting it to an even deeper idea called the master equation. In that framework, probability itself is fundamentally about geometric distance. The phase is just the distance traveled in our flavor space, the mixing angle is the rotation, and the probability is that squared projection. It's the exact same story, just in the language of formal physics.
Okay, so the geometric theory is beautiful, it's elegant, but is it true? How do we know this isn't just a clever analogy we made up? Well, let's turn to the hard evidence. Section 5, the Nobel Prize proof.
The proof really came in two huge steps. First, back in 1998, the Super Kamiokande experiment in Japan saw neutrinos that were created in our atmosphere disappearing as they traveled through the Earth, a clear-as-day sign of oscillation. Then, in 2001, the Sudbury Neutrino Observatory, or SNO, in Canada did something absolutely brilliant. They built a detector that could see all three flavors at once. And what do you know? When they added them all up, the electron, the muon, and the tau neutrinos coming from the sun, the total number perfectly matched what the theorists had predicted all along. The case was officially closed.
But here's the thing. Solving this mystery had a consequence that was, well, it was truly profound. It actually broke the most successful theory in the history of science. Let's look at Section 6, a crack in reality.
The logic is totally inescapable. The entire reason that vector rotates is that the different mass states travel at slightly different speeds, which causes them to get out of sync. For that to happen, their masses can't all be the same. They have to be different.
And there it is. The simple but completely earth-shattering conclusion from this whole discovery. Neutrinos, these tiny, ghost-like particles, they have mass.
And why is this such a big deal? Because for half a century, the standard model of particle physics, our absolute rulebook for the entire universe, was built on the core assumption that neutrinos were massless. The discovery of oscillation was the first, definitive, undeniable proof that this beautiful, perfect theory was incomplete. It was the first crack in an otherwise perfect wall, a crack that physicists today are still trying to peer through, searching for answers to even bigger mysteries, like dark matter and the very origin of the universe.
So, in the end, a simple problem of just counting particles led us to a truly profound truth. The transformation of a neutrino isn't some kind of magic, it's just a rotation through a hidden geometric space. And that suggests that maybe the universe doesn't just follow mathematical rules. Maybe the universe is geometry, all the way down. And if these ghost particles are busy tracing out the very shape of reality, it makes you wonder, what other secrets are written in its code?